Hi everybody. This video is going to cover what is the first part of chapter 9 in Newton. Be aware that there is no chapter 7 in Newton, so chapter 7 in your notes actually goes with chapter 8, and chapter 8 actually goes with chapter 9, and chapter 9 in the notes actually goes with chapter 10 in Newton. So there is no chapter 7 in Newton, so all these chapter numbers after 7 in your notes actually go to the next chapter up. So what we're going to cover today says chapter 8 in your notes um, on paper, but if you look at in your notes it says chapter 9, but when you pull it up it says chapter 8, but this is for chapter 9. Okay, so this is the beginning of chapter 9 on here. What we're going to talk about today is the sampling distribution of sample means, and I'm just going to jump right into it here. And this basically deals with the central limit theorem. Okay. For a relatively large sample size, the variable x bar is approximately normally distributed, regardless of the distribution of the variable under consideration. The approximation becomes better with increasing size. So, why is this important? This basically is telling us, well, let me back up. In chapter 8 of Newton, you are dealing with the normal distribution. And in order to do any normal distribution problem, you basically had to be told in advance in the problem that the distribution was normally distributed. Okay. This theorem tells us that if we make a distribution out of means, okay, out of means, so the whole distribution is nothing but a bunch of means, then that distribution will always be normal regardless of the shape that you started with. Okay. So it doesn't matter if the distribution is normal or J-shaped or uniform. If we take a bunch of means, sample means out of each one of these distributions and put all of those means into another distribution, in other words, we make a distribution of sample means, that distribution will always be normal. Okay. Which is pretty powerful because it means that any distribution, regardless of the shape, if we take repeated samples from that distribution and take the mean of those samples and then compile all those means into a distribution, that distribution will always be normal. We don't even have to check because the central limit theorem tells us that that distribution will always be normal. Okay, so that's where we're coming from in this. Now, really the only thing that changes formula-wise here is that the standard deviation of sample means is sigma divided by the square root of n. So before we had, let me get down here, z is equal to x minus mu divided by sigma. Okay, that's what you're using to find z-scores in the last chapter. In this chapter, it changes just ever so slightly in that z will equal x minus mu divided by sigma, which is divided by the square root of n. Okay. Now, if you're doing these in the calculator, you need to be a little careful in that we put parentheses around the numerator and parentheses around the denominator. Okay. So this is your formula for chapter 9, the first part of chapter 9. Let's look at a problem. It says mean weight gain during pregnancy. The mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain is skewed to the right normally. An obstetrician believes that her low-income patients gain more weight than the average weight gain. She obtains a random sample of 35 low-income patients and determines her mean weight gain during pregnancy was 36.2 pounds. Does her sample show that there might be something different about the low-income patients as compared to the national average. Okay. So we want to calculate the z-score. So in this case, sorry, get rid of that there. Okay. So in this case, z will be equal to, now, the mean that she's testing in here is that she obtains a random sample of 35 low-income patients. That's your N. The mean weight gain during pregnancy was 30, so that's mu. So let's write some of these down. Mu in this case is equal to 30. The standard deviation is 12.9 pounds. Okay. N in this case, the sample size is equal to 35. Okay. And her sample mean X is equal to 36.2 pounds. Okay. So we're going to do 36.2 minus 30 divided by 12.9. That is divided by the square root of your sample size, which is 30. Okay. So let's go to the calculator and find out what that might be. Okay. I'm going to do parentheses 36.2 minus 30 divided by 12.9, which is divided by the square root of 30. Okay, notice how I put the parentheses around the numerator and the denominator. I come up with 2.63, so that's 2.63 standard deviations above the mean. Okay, so we say to ourselves, do we think that her patients are gaining more weight than the national average? Well, her patients are scoring 2.63 standard deviations above what is normal. So do we think our patients might be gaining more weight than the national average? It does appear so. Okay. Now, we're not concluding any reasons as to why, but just going off of the raw scores, it does appear that our patients are gaining more weight than the national average. Okay. Now, moving on here. Let's do one more problem. As reported in Runner's World magazine, the times of the finishes in New York City 10K marathon are normally distributed with a mean of 61 and a standard deviation of 9 minutes. So if it says find the sampling distribution of the sample mean for a size of 4, the sampling distribution is always defined by just knowing, and this is always the case, what's your average and what's your standard deviation. Well, the average will remain the same. So the mean, mu, will still be 61. And then to find the standard deviation, we just do the standard deviation in 9 divided by the square root of 4, which we know is 2. So this gives us 4.5. Okay. So that's defining the sampling distribution. And you're going to do that a couple times here with some different numbers. Okay. Now let's look at an actual normal distribution problem using this method. Same problem, same mean, same standard deviation. It says determine the percent of samples of size 10 that will have a mean finishing time within 4 minutes of the population mean of 61 minutes. Now, within 4 minutes means plus or minus 4 minutes from the mean. So if I take 61 and do plus or minus 4 minutes, that will give me 57 as one of your x's, And if I add that to it, I'm going to get 65. Okay, so I actually have two X scores in here that we're going to be working with, but it's not a problem. So we have our normal distribution. Okay, we have a mean in the middle of 61. We have a score on this side, which is 57. We have a score on this side, which is 65. And they're wanting to know, okay, what percent of people will finish between those two times. So we're looking for a percent. Now, you can absolutely do this by hand, but it's much easier in the calculator. And just like in the last chapter with the normal distribution, all we have to do here is go to distribution, which is right above vars, normal CDF. Okay. The lower bound of this one will be 57. The upper bound will be 65. The mean does not change. We talked about that. That's 61. Now, the standard deviation is where you're going to see your change. And if we look at the problem here, it is a standard deviation of 9 with a sample size of 10. So we're going to put 9 divided by the square root of 10. Okay, and in this one, you got to close your parentheses on the square root. We go down to paste, hit enter again. So that is 0.84. So this is 0.84, or 84% of the runners will finish between 57 and 65 minutes. Okay. So what I tell people generally on this is, if there is a sample size, you need to use it. Okay, you need to use it by dividing by that sample size, like what we did up here at the top. Okay, standard deviation divided by the square root of n. So if there is a sample size of 10, if there's a sample size, you need to use it. Okay. We can do one here. Based on the Chevy Cobalt, engineers have found that miles per gallon in highway driving are normally distributed with a mean of 32 miles per gallon, standard deviation of 3.5. What is the probability that a randomly selected Cobalt gets more than 34 miles per gallon? Now, notice in this one, there is no sample size. So this is just going to be a regular normal distribution problem because they did not give you a sample size. So for this one, we have a mean of 32. Okay. And it says more than 34 miles per gallon. Well, I know 34 is going to be on this side. It's larger than 32. And more than will shade up. Okay. So that's what we're looking for in the first problem. So I would go straight to the calculator and say second distribution, normal CDF. The lower bound in this case is 34. The upper bound would be infinity. If you remember, that's a bunch of nines. The mean is 32. And, oops, sorry. The mean is 32. And the standard deviation is 3.5. Okay, 3.5. Let me get this back up here. So 3.5. Okay. So I get 0.283, let's call it 9. Okay. So it says as a probability, so we're going to leave that as a decimal. So there is a 0.2839 probability that if you select one car at random off the lot, that it will get more than 34 miles per gallon. So there's not a very good chance. It's about 28